Okay, want to look at the idea of basis of a vector space. I'm just going to start out with a very simple example. Set 1, 2, 3, 4 is a basis for R2. Why is this? Because this set is a linear independent set. Because it spans R2. That's very easy to prove that it's linearly independent. If we call this vector V1, call this vector V2, C1 V1 plus C2 V2 is equivalent to the matrix equation where the columns or V1 and V2 form the columns of this matrix. And we've done that pretty thoroughly. So if you don't understand this, you really need to go back and make sure that you pick it up, that you understand just exactly how that comes about. I'm actually going to kind of do that right now, but you have to make sure you understand this notation and why it is. Just to be explicit one more time. We can see that if we do C1, well, 1 times C1 plus 3 times C2, that's yeah, I'm going to have to go one more step on this. I did this before, and I really prefer I don't have to do it again, because you really need to have understood this previously so that we can go on to the next step. So if you don't totally understand this and didn't before I even wrote it down, you need to dig a little more, okay? So anyhow, we have this. And what is this? Well, C1 V1 is C1 times 1, 2. C2 V2 is C2 times 3, 4. And there's your C1 V1 plus C2 V2 equals your zero vector. And just to be even more explicit, I'm going to write the V1 here, V2 here. Okay, so we have these equivalences. You have to be sure you understand every step of that and recognize every one of these ways of representing the condition C1 V1 plus C2 V2 equals zero vector. Now, once we understand this, we can come back here. And if we understand that as long as this matrix has a determinant that's not zero, it's invertible. And when we multiply the inverse by 0, 0, we get 0, 0. So that C1 and C2 have to equal 0. Now I'm kind of out of space here. So I'm going to come over here. So I can say in particular, this is non-singular, meaning any one of many things equivalent to non-singular determinants not zero. The other equivalence is it's invertible. Non-singular, its determinant is not zero. Leave myself enough room there, didn't anticipate, but C1, C2 is the inverse of this matrix times 0, 0, which is equal to the 0, 0 vector. Now you absolutely have to understand matrix equations. You have to understand how a matrix equation represents a system of equations. Okay, and how in this case, the system represents this sum and the fact that this sum is equal to the 0 vector. And then you have to absolutely understand that you can invert this matrix, and you have to know how to invert matrices. You know, to take the augmented matrix with the identity matrix, reduce this matrix to the identity, which you can do if and only if the matrix is non-singular, and use it to solve the equation. Now, there are other ways to solve the equation, but you have to be able to do it in every possible way. Another way to solve it is to reduce the matrix 1, 3, 2, 4 augmented by 0, 0, which is the augmented matrix that represents this system, and review what we did in the last class or two. Okay, it's the augmented matrix that represents this system, something we did in the first week of class. And you can reduce that. And since this matrix reduces to the identity, and the zeros are going to stay 0, the solution to the augmented matrix is C1 equals 0, C2 equals 0. Now I've done that, so I'm not going to do it again, but just make yourself a note. And if you don't have it in your notes, you ought to be taking notes. If you don't have it in your notes, go back and review the video. We're only about 10 minutes into it. You can find this easily. You need to understand every detail of this. Okay. So anyhow, C1 V1 plus C2 V2 equals 0 if and only if C1 equals C2 equals 0. And I certainly hope that you recognize that this is the test for linear independence. There we have it. Now, the test is identical. If you have a set of 3 vectors in R3, you can do the same thing. Okay, you're going to have a 3 by 3 matrix because you're going to have to test C1 V1 plus C2 V2 plus C3 V3 equals a 0 vector. In R4 and R5 and whatever. And since any of the vector spaces we're going to spend most of our time studying are finite dimensional, polynomials, matrices, okay, the 2 main examples where the vectors are polynomials or the vectors are matrices, they can be represented by column vectors. Column vectors are no longer in Rn, whatever n happens to be, the dimension of your space, but they can be represented like that, and everything looks exactly like it does here, except that the bigger your space is, the bigger this matrix is going to be, and the more columns you're going to have for your constants. Okay, that's, you really, again, need to totally understand that. Okay, now, what are the implications of linear independence? Since they're linearly independent, now, if we have a set of vectors that we know is linearly independent and don't have to prove it, if it's already been tested, since the system is linearly independent, then I'm going to write the matrix in terms of columns. We know that the matrix is going to consist of the columns that represent the vectors. The V1, V2 matrix is invertible. So V1, V2, this matrix of columns, times 2 constants, okay, equals and I don't want to use X because that confuses notation. That confuses the notation with other representations. I'll use B1, B2. I could use any letters here I want. Some letters are more consistent with other notations that we encounter than others might be. So B1, B2 is a good choice. As solution, C1, C2 equals the inverse of this matrix of column vectors. Matrix whose columns are the vectors in the linearly independent set. You multiply the inverse of this times V1, V2, and you get a C1, C2. So that C1, V1. I'm going to move this over a little bit because the watermark could obscure what I'm about to write. C1, V1 plus C2, V2 equals B1, B2. That is, this B vector is a linear combination of V1 and V2. Now, what did we originally say? This is a basis because this is a linearly independent set. Well, we proved that. And because it spans R2. This is what it means to span R2. So we've shown I'd like to have a place to write this. We've shown, should have used a bigger board here, shouldn't I? Now I'm just going to kind of insert it where I've got a little bit of room to write here. All this is true, these two conditions. It's a linearly independent set, and because it spans R2, because this set is non-singular. And it's easy to test whether this is non-singular. You form the matrix and you take its determinant. Now I notice also, one of the questions I asked was expand a 4x4 determinant. Fairly simple one. That same question with different numbers was one that everybody seems to have gotten right when they did the homework. So again, there's this kind of mystery as to how people are doing really well on the WebAssign homework, but either aren't bothering to do the written assignments or don't know how to do them. This is getting serious because the midterm exam is scheduled for next week. We'll address that a little bit later. Okay. That's really what you need to know about basis. So the definition of a basis, just to make sure we understand. Definition is, it's a set of linearly independent vectors that span the vector space V. Okay. Now, a couple of consequences. These things are fairly easy to prove, and you're going to see the proof in the text. And I'm going to refer how these things are proved, but I'm not going to write out the proofs because they're written out in your book. I'm going to give you the idea behind the proofs so you can kind of look at the book then and see how the details work out. And I'm doing that just for sake of time. If we have time, I might come back and do a couple of those proofs. So we got this theorem. I'm going to state a little bit more in the vernacular. You can read the same theorem in your textbook. There exists a basis consisting of n vectors. Then every basis consists of n vectors. Okay, now we're probably about 25 minutes into the video. And you might want to make note of that because I'm about to tell you how this is proved without writing anything out. So if you want to hear my words, if you want to get my perspective on this, to give you a little guidance alternative to what the book says, because it's always good to have a couple of different ways something is stated. I'm going to just say this now. If you've got one basis consisting of n vectors, and now you've got another basis, okay, or another set of vectors, okay, that you think is a basis. And if you think this basis contains more than n vectors, well, all you need to do is write out all these n vectors in terms of the basis. I'm sorry, okay. Say it again. If you got a basis that has more than n vectors, or if you got a basis that has n vectors, okay, get the statement right. If you have a basis that consists of n vectors, then another set of vectors with more than n vectors, that set can't be a basis. And you prove that by writing out the members of that set in terms of the one you know is a basis. And you arrive at a contradiction. I have to write it out to make sense of any more than that. But the idea is you take the proposed basis, write it in terms of the known basis. If the proposed basis has more or fewer than n vectors, it's not going to work. It's not going to span the set, or it's not going to be linearly independent. Okay. So I guess I will write something out. Any proposed basis with more or fewer than n vectors if those vectors are written as linear combinations of basis vectors proves to either not be linearly independent or to fail to span V, so it isn't a basis. If you have more vectors in this proposed basis, then it must be linearly dependent. Cannot be linearly independent. It might also fail to span V, just on how badly it fails to be linearly independent, and you can think about what that might mean. Okay, so that's very important to understand this. Okay. All right. Well, now we want to get into some examples of bases. And there are these things we call standard bases. And we pronounce this word bases, not bases. Okay. Bases being the plural of basis. Okay. Standard bases. They're really, in a sense, the simplest possible. Each of these is going to be the simplest possible basis for the space. For R2, just be 1, 0, 0, 1. The matrix of column vectors is therefore the identity matrix. And I don't want to go into all the detail, but this means that your linear combination C1V1 plus C2V2 is just a column vector C1, C2. So that if this sum is equal to the 0 vector, then C1, C2 both have to be 0, proving that this is a linearly independent set. Furthermore, if you set this equal to any vector, B1, B2, let's say, then C1 equals B1, C2 equals B2. So it's very simple, the simplest possible basis. R3. Here's a basis. Now you can work out what C1V1 plus C2V2 plus C3V3 is, and I suggest you do that. It's going to equal then, you're just going to have a C3V3 on this, and you're going to have a C3 down here. Because C1 times this is going to give you the C1 up here. C2 times this vector is going to give you C2 in the second row. And C3V3 is going to give you C3 in the third row. So when you add these up, you get C1, C2, C3. All the standard bases are equally simple. For M22, which I hope you totally understand because you've done a lot of homework with M22. For M22, trying to write these words kind of compactly because I need just a little more room here. Not sure I'm going to get these in one line and keep it legible. It's 0, 0. I kind of automatically write an identity matrix when I start like that. Yeah, I think I'll squeeze it in. Okay. And in this case, I can write out what C1 V1 dot up through C4 V4 is. That's just going to be C1, C2, C3, C4. Now, if I want to express this as a set of column vectors, so I can do the matrix V1, V2, V3, V4 columns. I used A, B, C, D, but if I want to generalize, I better use subscripts. So let me change that. Not doing a good job of thinking ahead here. Okay. We can identify the matrix A11, A12, A21, A22 with the column vector A11, A12, A21, A22. And write the matrix V1, V2, V3, V4. Where this is V1, this is V2, this is V3, and over here we can barely read it at all. That's V4. Would be what? Well, 1, 0, 0, 0 put in a column is 1, 0, 0, 0. Zero, 1, 0, 0, you put in a column, A11 is 0, A12 is 1, A21 is 0, A22 is 0. Now you see how this is going to come out? Think about it for a second. You know, look at this, look at this. What are these vectors going to be and what do you end up with? Well, I'm going to just write it out. It's identity matrix. In four dimensions. And I haven't defined dimension yet, but you kind of get the idea. And I will define it after we do these examples. Okay. I hope I remember to define it, but I need to define it. So we can see that in this case, the matrix of column vectors is going to be 1, 0, 1, 0, 0, 1 with this column and this column together. Just make this into a matrix and remove these brackets and the comma, you get the identity matrix. In other words, the matrix V1, V2, analogous to this matrix, gives you the identity on R2. Similarly, this set gives you the identity on R3. And you get down here and you get the identity on a matrix that looks like R4. Looks like the identity matrix in R4. It is the identity matrix for 4x4 identity matrix, but we don't think of this as being R4 anymore. However, the space M22 is what we call isomorphic to R4. And we'll define that later on when we talk about linear mappings. Okay. So we can almost think of this as being 4-dimensional Euclidean space. It behaves exactly the same. The matrices look exactly the same. The operations look exactly the same. We're going to say up here that the matrix V1, V2, then equals I sub 2, the identity matrix in 2 dimensions. The 2x2 identity matrix, let's say that. Let's not use the word dimension until we define it. I'm not going to be able to restrain myself, but let's at least note that I should. Okay, here we have now 3 vectors in the basis. It's I3. And here we have 4 vectors in the basis. It's I4. So we've seen, now if we go back to what we said before, the theorem, if there exists a basis consisting of n vectors, then every basis consists of n vectors. In this case, we say that this space has dimension n. Okay, if there's a basis consisting of n vectors, every basis consists of n vectors, and n is then what we call the dimension of the space. Okay, so now I'd like to write it down here, and I guess I will just by moving this over a little bit. It follows that the dimension of R2 is 2, dimension of R3 is 3, and the dimension of M22 is 4. Now, the first exercises you're going to have in the homework will be to write out the standard basis for several vector spaces. Probably at least one of your questions will be identical to what we just answered here. But if you answer it, don't answer it without thinking about it. Don't answer it because, okay, I saw the answer in class, here it is. Because The next one might require you to think a little bit more, okay? You want to think it through every time you do it. I'm going to do one more example. I'm going to flip this board. Okay. The dimension of P4, the set of polynomials of degree 4, less than or equal to 4. Okay. And hopefully you understand what that is, because I'm not going to define it again. And presumably you've done the homework and you've worked with this space, so you understand exactly what I'm talking about. So the dimension of P4, and the camera isn't picking up the 4. Okay, dimension of P4 find a basis. And see how many vectors there are in the basis. Okay, well, the standard basis for P4 is, ouch, keep doing that. Eventually I'm going to develop some resistance in these knuckles. Okay, the basis for P4 is the set 1x, x squared, x cubed, x to the 4th. Now I'm not going to prove that this is a basis. I'm just going to assert it. You can work out why it is. But one thing that you can easily understand is why it spans P4. Okay. The span of 1x, x squared, x cubed, x to the 4th is the set of vectors well, linear combination. Arbitrary linear combination of this is just some constant times this, plus some constant times this, plus, and so forth. And call those constants C1, C2, C3, C4, C5. Such that C1, C2, C3, C4, and C5 are real numbers. Okay. Well, It's clear. Should be clear without comment that this could stand for any degree 4 polynomial, because what's a degree 4 polynomial? It's some multiple of x to the 5th plus some multiple of x to the, not x to the 5th, it's x to the 4th. Some multiple of x to the 4th plus another multiple of x to the 3rd plus another multiple of x squared plus another multiple of x plus a multiple of x to the 0, or just 1. There. So this is x to the 0, x to the 1, x to the 2, x to the 3, x to the 4. You can't have a polynomial of degree less or equal to 4 that doesn't have this form. Just write out the polynomial in standard polynomial form. If it's a factored polynomial, well, expand it into standard polynomial form, and you're going to see what C1, C2, C3, C4, C5 have to be for that polynomial, just the coefficients of your powers of x. So that should be clear. I said I wasn't going to prove this, but maybe I will. And then, so it spans. So say spans P4. Sorry, that's written poorly. And it's linearly independent. Which means what? Well, the zero polynomial, as you know from previous assignments, is just 0. Okay, 0 is the zero polynomial. To get the zero polynomial, you got to multiply every one of these basis vectors by 0, so that all the c's have to be 0. The only way this could be equal to 0 is if all the c's are equal to 0. And of course, V1 V2 up through V5 is here. And one thing you want to note about this space is that it's P4, but that 4 is not the dimension. The dimension is the number of basis vectors, and it's clearly 5. And that causes confusion. You saw me write an x to the 5th over here with C5, okay? You don't write, yeah, there's no x to the 5th in P4. But since you have the first constant being a multiple of x to the 0, it's the second constant that's a multiple of x to the 1, and the fifth constant that's a multiple of x to the 4th, and so on in between. So the dimension here is going to be 1 greater than the degree of the polynomial. Again, it's because the 0 degree polynomial, multiples of x to the 0 or 1, is part of the space. Okay. Now there's something I said I was going to do, and I don't remember what it was, but hopefully it'll happen. Anybody want to remind me what I said I was going to do and was concerned about whether I'd remember? I might have already done it. Okay. There we have it. Well, that's the standard basis. Okay, and these right now are the only types of spaces that we've really looked at. So any question you have about a standard basis will be a question about one of these spaces. I'll reiterate that the number of vectors in your standard basis is the dimension of your space. So down here, I'll make a big important statement. The fact that there are 5 vectors in the standard basis implies there are 5 vectors in any basis, which implies that the dimension of P4 is 5. Lower the camera a bit. And just in case the watermark is obscuring that, here we have it. Okay. Okay. Now there's more to it, but not all that much more. We can look at other bases. Okay. Other bases for deciding which space I want to look at. Okay, for R2, just to kind of do these in order. Actually, I'm going to do R3. I've had this sitting here. Because I do want to get into the geometric aspects of the idea of basis and span. Okay. Let's say we want to look at this set of vectors and see if it's a basis. Okay. Just looking at notation and also looking at the camera. Maybe get some room over there. Okay. I started last time, and then when I look back, I realized that you haven't really been asked to do this. And it's been about 10 or 12 minutes trying to sort my way through this, realizing that I hadn't anticipated that it was going to require more machinery than we had to do what I thought you're going to be asked to do. And so I look back and see what you were asked to do and find out that you weren't asked to do it. So I think I put a little blurb on the description of the video from last time. You should probably ignore that 12-minute section, whatever. So hopefully you noticed that if you looked at the video. Okay, so what I started to do was specify what the span of this space is. But let's use that as an example of testing whether this is a basis. Okay, first of all, call these vectors v1, v2, v3. So the span of these 3 vectors is v1, v2, span of v1, v2, v3. C1V1 plus C2V2 plus C3V3 equals this times this. Okay, the set of all vectors you can get. Okay, let's say it again. This expression is this, and that should be very clear. If it isn't, you need to go back and make sure it is. In three-dimensional space, and I'll just use X, Y, Z instead of X1, X2, X3, which is what we would usually use if we wanted to think of expanding this to higher dimensions. And remember, higher dimensions, we can't draw a picture. We can't visualize it. We live in three-dimensional space. We still do work in it, still do geometry in higher dimensions, and that gets really complex, and I haven't done much of that, so I just accept that it gets really complex. Sort of a specialized field, important, specialized. Okay, so I'm going to use X, Y, Z instead of X1, X2, X3, but I probably ought to use X1, X2, X3. Except that X, Y, Z is familiar, so I'm going to use it instead. You see here, we have the equation stating that a linear combination of C1, C2, C3 is equal to just any old vector X, Y, Z. And the question now is there that's always, the S is kind of small. Okay. And I'm going to remove the word always. Is the linear combination of V1, V2, V3 equal to X, Y, Z? Well, this matrix is just a column, the matrix of column vectors. So we have this matrix. It's singular. Determinant is 0. Not invertible. Can't write. The solution to this, in terms of the inverse, since the inverse doesn't exist. Okay, so what are we going to do? Well, inverse doesn't exist. So what we do is we row reduce the augmented matrix. Augmented matrix is this. And we can row reduce the augmented matrix. We can row reduce it rather quickly. So guess what? If I use the 1 here to eliminate the 2 and the 3 down here, and I'm not going to write all the details, I have to assume that you're very familiar with row reduction and know how to do it. And from the work I've seen, that seems to be more or less the case. There's one person I haven't gotten any work from, so I can't tell. But even people who didn't do particularly well on a certain assignment seem to have done okay with the row reduction. Now, might be you went to Wolfram Alpha and got that row reduction, which is not the way to learn. Okay, so I don't know. But I tend to think that everybody's okay with row reduction. So we got 1, 3, 1, x. Then we're going to have 0 here, subtracting twice the first row from the second, and -4 and -1. And that's going to then have y minus 2x. And then we're going to have 0 and -11 and -3 and z minus 4x. Not 4x. I'm not sure where I got 4, but these numbers kind of act like, don't know why I used 4, but I did in my feeble head here. Subtracting 3 times the first row from the second, we're going to have -8, -2, so forth. Okay. Well, if we then subtract twice the second row from the third, we're going to get all zeros here. Now here, what do we get? We're subtracting twice this from this. This is going to be z minus 3x minus twice the quantity y minus 2x. Okay, again, this minus twice this. And that is going to lead us to, and in this step, we'll simplify the expression here. So we're going to have what? Minus 3x plus 2x is x. We have a minus 2y. Plus z. Now we could go on, we could subtract 3 times this from this, and maybe we'll do that. But right now, let's focus on the fact that this has to be 0. This is the equation of a plane in 3-dimensional space. It's a plane that we can easily visualize. Let's consider it for a minute. Okay. Put this in a different color. The plane here. Okay. If y and z are both 0, meaning that you have to be on the x-axis, because if y is 0, you're in the plane of x and z. And if z in addition is 0, you're right on the line where x, well, you're right on the x-axis. Oh, shucks. Can't do what I wanted to do. And that was kind of ignorant of me because I know perfectly well that this is a plane through the origin. Okay. So, okay, if y and z are 0, x has to be 0. Clearly, the only way this can be 0 is if it's a plane through the x-axis. And it's going to be a little more difficult for me to visualize this. I mean, I know that the vector perpendicular is going to be the I vector 1 unit in this direction, minus 2 times the j vector, 2 units in this direction, plus the k vector, 3 units in this direction. So if we come out to here, and then over here, 2 units, and then up 3 units, that's going to put us about here. So now we have a vector from here to here. And that vector is, okay, that vector projects down to the xy plane here. So you can kind of visualize where it is. I can draw a rectangle around it and so forth, but I won't. Just giving you a little preview of what you're going to see in multivariable calculus. It's not difficult. Now I made a connection here. I'm not going to explain it, but this vector is perpendicular to the plane, and the plane goes through the origin. The vector kind of in 3-dimensional space kind of comes out 1 unit in the x direction, 2 units backwards in the y direction, 3 units up in the z direction. So it's kind of in this direction here. You can see where that is. The plane is perpendicular to that down here. So the plane is kind of like this through the origin. Okay, well, that's a geometric interpretation. And I probably want to do a little more geometric interpretation. I'm not going to have time to do today, so I'll probably append that to the video I owe you. But in any case, for any solution, we have this, it's the equation of a plane. Now we can go on and solve for, well, we can eliminate the 3 up here. By subtracting 3 times this from this, which is going to give us 1, 0, 1/4. And now we're going to have x minus 1/4 of this. That's our x minus 3 times this. I'm going to run out of room. You might want to write it out yourself. This x minus 3/4 is a quantity y minus 2x. In other words, this minus 3 times this. And then we're going to have 0, 1, 1/4, which is still our y minus 2x over 4. And we're not going to change this. Now our conclusion is that this stands for, well, looking at room and stuff like that. This stands for y minus 2x over 4 equals, if you go back to the equation, we're trying to find C1, C2, and C3. So this is C2 plus C3 over 4. And this is, well, x this is C1 plus C3 over 4. So we have 2 equations and 3 unknowns. If we let C3 equal T, then simplifying this, we get y minus 2x over 4 equals C2 plus 2 over 3. And here we get, what is it, x plus 3/4 of 2x is plus 3/2 x. So we get 5/2 x minus 3/4 y equals C1 plus 2 over 4. This should be 2 over 4 here. Okay, well, this is going to lead to some equations that tell us 2 vectors that span this plane. Okay, don't have time to finish this. But now there are 2 vectors that span the plane. The plane is down here, and there are 2 vectors that I don't want to. It's not going to represent the 2 vectors appropriately, but we're going to get 2 vectors out of this that span the plane. So you can see how this works out. And I actually don't remember. I don't think that you actually have to do this for the present assignment. This kind of anticipates what you might encounter a little bit later in the subsequent assignment. But if necessary, I'll kind of finish this up on the video that I hope to have for you by tomorrow. I'm going to give you through the weekend to get the current assignment. I'm going to stop the recording here.